Okay, so the goal of this lecture is going to be kind of an overview of null hypothesis statistics testing and trying to help you to understand what null hypothesis statistics testing is, why we do it, and how we can use it to interpret the statistics that we perform. So far, a lot of what we've looked at has been descriptive statistics. These are measures of central tendency and variability. What are the mean, median, and mode of our data? What about the range and the standard deviation? What do the scores on this specific exam look like? And how do your scores compare to the scores of your classmates? But this doesn't actually allow us to know or attempt to know anything beyond the data that we have on hand. From there, I moved into some theoretical statistics. The main ones we've covered here were things based on the normal distribution, such as Z and sampling distributions. These were useful in helping us to be able to see percentages and probability, but they required us to know some population parameters. And unfortunately, in research, we very rarely know the parameters for the population. What we have to do is make inferences. These are educated guesses about what the population parameters would look like. If I measured every college student's sleep habits, what would they look like? Does this medication work for everyone who has depression? What is a normal range of motion for a person's wrist? Do people like this new and improved version of a product? To do this, we have to use inferential statistics. And we've already done this a little bit. Remember, we talked about inferring the population standard deviation by the sample standard deviation. And remember that because we were making an inference, we had to modify that formula a little bit to account for the likelihood of our sample mean not being the same as our population mean. We did this by using a more conservative measure for our denominator, which increased our standard deviation. So you can see that here in this formula. One of our main goals with inferential statistics is to identify potential differences between populations or links between variables. That's what we're going to be spending most of the rest of this semester doing. It's great to know how students do on an exam and how you compare to the other students on that exam, but it's probably far more useful for you to know if students who took Math 217 do better in their upper level courses than students who took Psych 217, this course. Or to know how well performance on exam 1 predicts students' overall grades in the course so that you can decide whether or not you want to drop the class after bombing the first exam. This requires us to make assumptions about the population, including future students in the course, based on past samples. I can't know how you will do on later exams or in future courses, but I could tell you how past students did and let you draw conclusions based on that. Now, there's always a possibility that the samples are not representative of the population and that they're somehow biased to do better or worse. There's also the possibility that our sample is representative, but it's just in that extreme 5% that we're excluding in our 95% confidence interval. This is why replication is so important and why we can't just assume that because it was true in one sample, it will be true for the whole population. Talking about null hypothesis statistics testing, but first we have to start off with what is a hypothesis? Now, you're probably already familiar with what a scientific hypothesis is. We use the term hypothesis all the time in everyday language to mean just a guess. But a scientific hypothesis is a statement or proposed explanation for an observation, phenomenon, or or a scientific problem. In other words, it's an attempt to explain or predict an observation or question. To be a scientific hypothesis, it has to be testable using the scientific method. Saying that I believe that when we die, we become bison living in Montana is not a scientific hypothesis because it's impossible to test. If you haven't already, you'll likely take some sort of research methods course in the future, and you'll learn so much more about hypotheses and scientific theories, so I'm really not going to spend too much time on that here. But one thing I do want to point out is that hypotheses are often statements about the value of a population parameter. We might hypothesize that cats are smaller than dogs. We would test this by measuring the size, such as the mass or the height, of a sample of cats and the size of a sample of dogs in order to determine whether cats are smaller than dogs. We use our sample data and we make the assumption that our sample is representative of the population. Therefore, if the cats in our sample are smaller than the dogs in our sample, we assume that the difference will hold true for the populations of cats and dogs. Another example of estimating population parameters would be saying that college students spend more time on social media than high school students. I need to know how much time each group spends on social media so that I can determine whether or not they are the same or different. Determine whether they are same or different. Finally, we can look at the claim that millennials aren't having kids. Obviously, this isn't true in a very literal sense. You can see this by the existence of Gen Alpha kids, who are mostly the children of millennials. So some millennials are having kids, but as a whole, do millennials have kids or not? We can use statistics to evaluate this claim. We can also use the statistics to evaluate the claim that you used in a previous homework. Does Raisin Bran cereal actually include 2 scoops of raisins in each box? You've already evaluated this by establishing the mean, standard deviation, and confidence interval for the sample data provided. But now we can dig into how those different steps you did are part of a statistical process for evaluating differences. It's important to first keep in mind an important thing about scientists. We can be obnoxious and pedantic. We will say something is theoretical even if all of the evidence backs it up. That's why evolution and gravity and germs being the cause of illness are all theories instead of being laws, because we can't actively see them exerting their effects, and we haven't run every possible version of every possible test. So we won't state that it has been proven true because it hasn't been to the level that science requires. And this is because proving something means that we know 100% that it is absolutely true. For example, I could never prove that pigs cannot fly. To do that, we would have to evaluate every single pig that ever was, ever will be, to make sure that they aren't capable of flying. We also need to evaluate them in every possible location at every moment of their lives, because just maybe, had we dropped that one pig from a height of 3 feet and 5.2 inches on February 1st, 538 BCE, in what is now Hanover, Indiana, and the sun was in an eclipse, and the pig had just been bitten by a mosquito, it would have been able to fly. We can't test that. We haven't tested that. And therefore, we cannot say that pigs cannot fly, because that's we don't have all of the tests done. Now we can disprove things. If we find a flying pig, that can disprove our hypothesis that pigs cannot fly. This would lead us to reject the hypothesis that pigs cannot fly. We can also fail to disprove things. If we test every pig ever and find no evidence of flying, we fail to disprove our hypothesis that pigs cannot fly. But this does not mean the hypothesis is true. It just means our data don't lead us to reject it. This is the essence of the phrase absence of evidence is not evidence of absence. Just because we have no documentation of it ever happening does not prove that it has never or will never happen. Now, another obnoxious but very important aspect of scientific thinking is that we assume that there is no effect until we have evidence that refutes that assumption. This is the same basic idea as innocent until proven guilty. as a scientist, I think this medication works, but I have to assume that it does not work until we have evidence to the contrary. Because think about it. If we assumed that it worked and we were okay with just assuming that things work unless we have evidence that they don't, we wouldn't do any testing because at best, the testing would confirm our expectations that the medication works, but at worst, it would contradict it. We would not actually benefit from doing the research because we start out saying, yes, it works. And the really one of the only outcomes that's going to change anything would be evidence saying it doesn't. So instead, we need to assume there is no effect, that the medication does not work. And to make any kind of claim that there is an effect, we have to provide evidence that the no effect stance is wrong. This leads us to a process called null hypothesis statistics testing, or NHST. NHST is a blend of two different approaches, probability and competing hypotheses. First of these is probability. Now, Ronald Fisher is arguably the father of probability. In fact, we'll soon start talking about Fisher's p-values for just about every single test that we do, though we'll typically shorten them just to the name of p-values. You've already done some stuff on probability, including estimating the probability of a particular score occurring given the mean and standard deviation. But let's dig a little bit more into the logic of probability. Now, Fisher described an experiment meant to test some lady's claim that she could tell just by the taste whether tea was added to milk or if milk was added to tea. So basically, did they pour the milk into the cup and then add the tea to the milk, or did they pour the tea into the cup first and then add the milk to the tea? He thought he could give her a few cups of tea, half of which had the milk, then the tea, and the other half had tea, then milk. Now, if he just, and so she would taste them and she would tell him which one was it. Now, if he just gave her a single cup, she would have a 50-50 chance of getting it right. But what about if he had her taste 6 cups of tea, 3 of which had milk first and 3 of which had tea first? That would be 20 possible orders. And you can see those orders over on the right-hand column here. So that's what this is. So T meaning tea first, M meaning milk first. So this first one, it was milk, then tea, milk, then tea, milk, then tea, and then tea, then milk, tea, then milk, tea, then milk. So you can see those there. So what is the probability of her getting them right purely by chance? Let's say she took a wild guess and wrote down an order beforehand. She just randomly picked one of the orders from the column and decided those would be her answers. She would have a 1 in 20 chance of being correct purely by chance, or 5% probability. This is way less likely than that 50-50 chance if it was a single cup. So Fisher was interested in the probability of things happening purely by chance. And if the probability of them occurring by chance was really low, that provided us with some degree of evidence that it wasn't purely by chance. So if you had a 1 in 20 chance of guessing the correct order and you actually guessed the correct order, then there's a decent chance it wasn't purely chance. So let's say this tea lady was correct in her assessment of each cup of tea and whether it had tea then milk or milk then tea poured into the cup. The probability of this occurring but purely by chance is only 5%, which is pretty unlikely. And that lends support to her argument that she is able to taste a difference in the tea depending on the order that it was poured. Next, we have hypothesis testing. Now, Jerzy Neyman and Egon Pearson believe that instead of just looking at probabilities of something happening, we should be making scientific and testable statements or hypotheses. And each hypothesis should be split into two: an experimental or alternative hypothesis and a null hypothesis. The experimental or alternative hypothesis is exactly what you expect. Most of the time, this is going to be that there is some sort of an effect or difference. In Fisher's tea tasting experiment, the alternative hypothesis is that the lady could taste a difference based on whether the milk or the tea was poured first. In contrast, the null hypothesis is a lack of any effect. That's why it's called the null. It means nothing. In the tea tasting experiment, this would mean that she could not actually taste a difference in the teas and she was purely guessing. With this method, we have our expected hypothesis that she can taste a difference. But remember that we can't prove someone innocent. We can only find them guilty or not guilty. So instead of trying to accept our alternative hypothesis, we test the null and either reject or fail to reject it. Now, finding someone guilty does not mean that they are innocent. It just means that we failed to provide enough evidence to show that they were guilty. Similarly, rejecting the null hypothesis does not mean that the alternative hypothesis is necessarily true. That is one possibility, but all we can actually say is that we did not have enough evidence to not reject the null hypothesis. The problem is that this two hypothesis method doesn't actually give us any hard and fast rules about how to test the null and how to, when we reject it or fail to reject it. What level of evidence do we have to have in order to reject or fail to reject the null hypothesis? This is where Fisher's probability comes in. Putting these two pieces, hypothesis testing and probability, together gives us null hypothesis statistics testing. We provide two statistical hypotheses. The alternative hypothesis states that there is a difference or an effect. If we have two groups, they are quantitatively different enough that they belong to two different populations. If we have a predictor and an outcome, the predictor has an effect on the outcome. The null hypothesis states that there is no difference or effect. We're looking at two groups. There are no differences between the groups, and they are from the same population. Our predictor does not have any kind of effect on our outcome. We test the null hypothesis using probability statistics. What is the probability of us getting a particular result if there is truly no difference or effect? If the probability is low, we reject the null hypothesis. Again, this does not mean that we are accepting the alternative hypothesis, because saying that we accept the alternative would be roughly equivalent to saying that it is true, and again, we can't know that for sure. But we can say that it is unlikely that the opposite is true. Again, scientists are pedantic, and this may seem really obnoxiously tiptoeing around. And yes, so many people, including so many statisticians, agree that it is really dumb that we do all of this. And so if you're feeling frustrated and annoyed by this, know that there are a lot of people agreeing with you. But this is the way we do this type of statistics testing. So if that probability is low, we reject the null hypothesis. Now, a long time ago, Fisher set a cutoff for what we should consider likely or unlikely, which is 0.05. This probably sounds familiar because you looked at it with the z-scores already. That is that 5% cutoff. Remember, 5% is also the opposite of 95%, which is what we established as our confidence interval already. This cutoff, whether it is 0.05 or 0.01 or 0.001, this cutoff is typically referred to as your alpha level. Now, it's important to know that this 0.05 is pretty much arbitrary. Fisher picked it a long time ago, and even he said that it should not be the gold standard, but that's how we ended up treating it. Some disciplines have other standard cutoffs, such as 0.01, meaning that we have 99% confidence, and others reject the probability approach altogether. We have these two hypotheses, right? But why are we bothering with two statements that are the opposite of one another? Why not just test the question we actually want to ask? Again, it comes down to the fact that we can't prove anything in science, because proving something means that we know 100% that it is absolutely true, but we are working from sample data and cannot know the parameters of the population. Without knowing the population parameters, we cannot know if we are correct. But we can estimate the probability of a statement being true. But to do that, we need to have a value to compare it to. Let's say we want to know how cats and dogs compare intelligence wise. You might have a hypothesis that the species an animal is has an effect on their intelligence and that they are two different populations. So, cats and dogs are different populations, have different distributions in terms of intelligence. But in order to test that mathematically, you need a value to compare it to. So you need to say that cats are 1 point or 100 points or 1 million points smarter or dumber than dogs. You would have to test every possible iteration. It's much more straightforward to test the assumption that there is no difference between cats and dogs. Because by doing this, you can say, here is a presumed range for dogs, and here is a presumed range for cats. What is the likelihood that their means, that the population means, would fall into the same range? If they fall into the same range on intelligence, we can say they're from the same population intelligence wise. If they're 95% confidence intervals, indicating the likely population mean, are pretty far from one another, we can say that it's unlikely that cats and dogs are part of the same population. Now remember, we can't accept a statement as true, but we can reject a statement as being unsupported. So if we find the statistic for cats and dogs are far enough apart, we can reasonably say they're probably not from the same population intelligence-wise. In other words, we can say that the assumption that species does not predict intelligence is not supported, and therefore we reject the null. In contrast, if we find the sample statistics for cats and dogs are pretty similar, we fail to reject the null hypothesis. Now, again, we're not saying that cats and dogs are the same. We're just saying that we're not rejecting that idea. Again, scientists are a little bit annoying for all of this, and a lot of people disagree with this approach. So I hope you're not getting too frustrated with this. So here are the basic steps of null hypothesis statistics testing. First, you set your alternative and your null hypotheses. Then you set your probability level and identify the corresponding critical value. Then you calculate your statistics, and then you make a decision about whether or not you're going to reject the null hypothesis. Now, we haven't talked much yet about alpha or probability levels. Like I mentioned before, Fisher somewhat arbitrarily picked 5% or 0.05 as a reasonable amount of uncertainty, which is why we use the 95% confidence interval. But we aren't married to that number. Some disciplines like to use different alpha values, and at least in psychology, we're in the process of moving away from a strict probability level and instead treating it as a sliding scale during interpretation. And that will make a lot more sense. That statement will make a lot more sense once we're actually doing the statistics. Now, when you calculate the different types of statistics in this course, most of them will require you to look up what's called a critical value. Think of the Z and T scores you used last week. If you look back at Appendix C, you'll see that there are lots of different tables listing critical values based on alpha levels and degrees of freedom that you have to work with for different types of tests. So you'll see critical values for t-tests and for f-tests and for chi-square tests and things like that. As we go through the different statistics in this course, you'll learn to calculate different types of scores. If your calculated score is greater than the critical value that you looked up in the table, then you have what is referred to as a statistically significant effect at whatever alpha level you used, 0.05, 0.01, whatever. Hopefully, this helps to make a little bit more sense of null hypothesis statistics testing. Again, there's a lot of debate about the approach that null hypothesis statistics testing takes. If you go on and take additional statistics courses or things like that, you will probably learn about Bayesian statistics, which is a completely different approach to running your statistics and how you interpret them and things like that. But null hypothesis statistics testing is still the most commonly used method of analyzing statistical results.